right, let's talk a little bit about MXFP8 training for MoEs with TorchAO. For context, now these are the same slides I presented at the PyTorch conference recently, but this will just be a little bit more of a detailed talk through them since the conference I only had like 7 or 8 minutes to speak, so it was very concise. So here we can kind of have a little more relaxed presentation and talk through them. So let's get started. First, just a quick refresh of what MXFP8 is. It is a low-precision numerical format with native acceleration for certain operations on Blackwell generation GPUs. Couple key characteristics of it are, one, the data itself is an FP8, specifically E4-M3 format, so that's 4 exponent bits, 3 mantissa bits, and the sign bit. And then the scales for that data are also an FP8, but an E8-M0 format, which is 8 exponent bits and 0 mantissa bits, so that's power of 2 scales in effect. Other key characteristic is that the scaling granularity for that data is quite granular, basically. It's 1 by 32, which means that it's pretty good for preserving numerical accuracy during training because basically the impact of any outlier in your data will be limited to only affecting the scaling factor for the 1 by 32 block that it's a part of, right? So if you have an outlier somewhere in this block, causes the scaling factor to blow up, leads to high quantization error when you're rescaling back to original precision. It's information loss, bad for stable training dynamics and numerical integrity relative to your high precision baseline. That quantization error, that blown up scaling factor only affects the 1 by 32 block here, not like a whole row or a whole block or a whole tensor, or that you might see basically with a more coarsely grained quantization strategies like blockwise or rowwise, etc. So yeah, that's the TLDR on MXFP8, and this is how we are using it to accelerate training. We are doing something called dynamic quantization, which is illustrated very crudely here by me. Basically, instead of a BF16 group gem for computing our routed experts in an MOE, we dynamically quantize the inputs to that group gem operation to MXFP8, which you can see in the green here, and then that allows us to do an MXFP8 group gem, which can achieve a 2x speed up over a BF16 group gem baseline. So as long as your quantization kernels are sufficiently fast and your MXFP8 group gem is implemented well, you should achieve a net speed up over the BF16 baseline, as you can see here in the red. And that is what we have implemented in TorchAO, and natively integrated into Torch Titan as well. So you can just kick it off with a pre-training run there with a command line flag if you'd like. You can also directly use the TorchAO APIs yourself. It's called 2MXFP8 and scaled grouped MM, and it does exactly what it sounds like. It's a differentiable drop-in replacement for torch.groupedmm. So it makes it very easy to just experiment with and try out for training right out of the box. Have some benchmarks here with some Llama 4 shapes and DeepSeek V3 shapes. On micro benchmark of just this primitive op, the net speed up, so the dynamic quant and scaled group gem, is 1.6 to 1.8x over a BF16 group gem baseline. And for a single MOE layer on a single B200 with the config seen here, we see 1.42x speed up over BF16 with Llama 4 shapes, Llama 4 Scout, and then 1.18x speed up over BF16 using the DeepSeek V3 shapes for the big model, the 671B. And that's because these DeepSeek style experts are smaller and skinnier, which are just a little bit worse for dynamic quant and gem efficiency and whatnot, which I can talk about more if anyone would like, but yeah, that's for now. We'll just move along. End-to-end training benchmarks, we have natively integrated into Torch Titan, as I mentioned, and with a single node training benchmark, I just want to be clear about that. I was constrained to only doing single node benchmarks with 8 B200s connected via NVLink with the configs you see here. But it's still a representative benchmark, still useful, I think, because all I did was reduce the number of layers to prevent OOMs. All the other model configurations and training configs are fairly representative of a real training run, so still useful data here. We see a 1.48x speed up in the early stages of training where there's like an imbalanced expert load. And then 1.21x during steady state training where there's like a fairly uniform-ish expert load balancing. So I looked into this discrepancy, and it turns out it's because the MXFP8 group gem, the Cutlass kernel we dispatched to, performs particularly well when relative to the BF16 group gem when the M dimension is very large. And M is our local batch size times our sequence length, and so you can imagine with imbalanced expert load, say one expert receives all the tokens, that M dimension is going to get very large. So it just turns out in these scenarios that it performs especially well, so you get an extra speed up during that. So yeah. Next, that's how we are speeding up computation for MOE training, but we're also looking at comms and speeding those up because MOEs are famously comms heavy, and so we have a couple in progress APIs here. One is called 2MXFP8 alt-all dequant, and one is called 2MXFP8 on-device alt-all dequant. I'll talk through the differences briefly here. The first one is just a drop-in replacement for alt-all single from PyTorch core. Both these APIs dynamically quantize the inputs to the alt-all to MXFP8, do the alt-all with both the data and the scales, and then dequant on the other side, dequantize to get original precision. The trade-offs between these two APIs are one, this one requires no token dropping in your modeling code, but does require a device to host sync because your input and output splits, which are arguments to an all-to-all operation, must be on the host. And this is because in PyTorch core we are dispatching to nickel all-to-all under the hood, at least for the vanilla implementation, and that requires that these are host-side arguments. Okay. Alternatively, we have this other one that is implemented via a custom Triton kernel and symmetric memory APIs that does all of this on the device. So the input splits, which are, remember, these are the input splits define like on a given EP rank which tokens are going where essentially, and they are derived from our router scores, which of course are computed on the device, right? And in principle, we should be able to have a kernel that does the exchange of our input splits between the EP ranks, exchange that metadata to get our output splits, which define, where all the data ends up, like, on a given EP rank, how many tokens I'm receiving for each of my local experts, so that I can allocate memory accordingly and do, all the subsequent operations. And that's what we've implemented here with Triton and symmetric memory. So no host-to-device sync is required here, which is great for performance. And again, it's differentiable just like the other one. And the difference, though, is that there's token dropping required. So, just some trade-offs, some impact there on data efficiency you might want to think about, the modeling practitioner, it's their decision. But the reason for this, perhaps we can talk about this, it's a bit, some interesting details here, why this trade-off exists. Basically, in the implementation of this with symmetric memory, the way it works, you have to pre-allocate symmetric memory buffers in your device memory, and you do something called a rendezvous, which involves creating these handles for these buffers and exchanging these handles amongst ranks involved in the symmetric memory allocation and rendezvous to register them into the virtual address space of your local device. So that when on my local device I write into that virtual address space, the symmetric memory infrastructure basically can use multicasting to do the data transfer between my local rank and the target remote rank where that symmetric memory buffer is registered to. Okay, so this is a non-trivial operation. This rendezvous. It's expensive basically, and so we only want to do it once at the very beginning of training, which means we cannot be dynamically allocating symmetric memory buffers based on how many tokens my EP rank is going to receive on this particular layer on this particular training step, right? So you just have to use a heuristic and just say, when you pre-allocate at the very beginning, you say, I am defining that I don't expect to receive more than X bytes or X number of tokens. You would over allocate some, say like 1.5x over what you'd expect. But if in training that turns out to not be enough and you're deep into a pre-training run, you need to have token dropping code implemented to handle this without crashing. so that because basically if um, you end up receiving more tokens than you allocated for your symmetric memory buffer, you would either crash or need to do token dropping. So token dropping is the preferred solution, obviously, and it's like a real solution. It's not like some hack. It's this is something that real training runs often do for efficiency reasons, and I won't get into a bunch more detail here, but basically, just another interesting fact is that it's not just the input tokens. We need symmetric memory buffers for those. Basically, anything that needs to be exchanged across ranks in all-to-all, forward and backward, needs to have a symmetric memory buffer for it, right? So in the forward, that's going to be our input tokens, right? Because we're going to be exchanging those across ranks, and also our input splits, right? So we're going to be exchanging input splits first to compute our output splits. Then using that information, we are going to do the actual data transfer of the input tokens, right? This is all in the forward pass. So we need symmetric memory buffers for those. Then in the backward pass, our upstream gradient comes, right? And the gradient of the output is going to, its size, it's going to be dependent on the output during the forward pass, which again is variable based on the router scores that were computed during the forward pass. So we now have this variable size upstream gradient that needs to be, rerouted back to the home from which the gradients for that token, the gradients for each token need to be rerouted back to the EP rank from which they originally came to proceed with backprop, right? So this is data exchange. This needs to be implemented with the symmetric memory buffer as well. And so you have these symmetric memory buffers for both forward and backward, and the backward one in particular for the gradients, that's variable in size, right? So, the pre-allocated buffer itself is not variable in size; it's statically sized. But that's the problem, and the size of the data we're writing to it is variable. So that's where we need to have handling for this basically. But you can see in the Torch Titan experiments directory, there's a DeepSeek v3 implementation that uses this. It uses a BF16 version of this, but it's the same concept. The MXFP8 version here is just a customization of that same kernel. So, but you can see an example there of how you would implement safely something like I'm describing. Okay, cool. So that's that, and the status of this is just it's numerics correct, functionality correct, validation end to end in Torch Titan with good, stable convergence relative to BF16, identical convergence, all done. Problem is the speed up is not good because it turns out the dequant operation here is redundant and killing the gain. So basically, I implemented it with dequant at first just to make it easy to, this is like a starting point, it can easily be plugged into the training code without any modeling code changes because, we're going to get out a BF16 torch tensor here, and that's what all the subsequent modeling operations expect. But the problem is the order of operations here is all to all, right? Exchange, send tokens to where they need to the device where the assigned expert lives, then do a token shuffle on each rank locally so that the tokens we've received are sorted into the same order that the experts are stored in, so that we can then efficiently do a group gem, right, and compute our routed experts output. But if we look at the operations here, it's all-to-all, dequant, token shuffle, re-quantization, then MXFP8 group gem, right? So there's a dequant and then a requant. And that redundant, no op there is killing the performance gains, basically. So the speed up is small and it should be much larger. So what we need, how do we solve this? We need a token shuffle kernel that can reorder the tokens to be reorder the tokens and the scales together. It can operate on MXFP8 data basically, and then we need the MXFP8 this API to MXFP8 and scale group MM to optionally accept pre-quantized inputs. Okay, so we can stay in MXFP8 through the all-to-all, through the token shuffle, and then through the group gem, and then get our rescaled outputs in BF16 on the other side. So only quantize once and never dequantize until the end. So yeah, stay tuned for that. We'll share an update once it's ready. And then now, for the fun part, we can do a quick walkthrough of an illustrated walkthrough of how this actually works under the hood. The forward and backward paths of a dynamically quantized MXFP8 group gem. So this is the fun part, I think, where we get some nice diagrams to help us visualize and make things more concrete. So we start in the forward pass. This is the group gem and the inputs to it. Our left-hand side operand is the input X, our input activations. It's going to be 2D with an offsets tensor, which defines the end of each token group, right? So as I mentioned previously, we have shuffled, and so that our tokens are grouped in the same order as the experts are stored, so we can efficiently do a group gem. And then here are experts weights, which are 3D tensor, where each is just a linear projection, but they are stacked into a 3D tensor. Now our first step here for MXFP8 group gem is to quantize to MXFP8. So you can see inputs 2D get quantized to MXFP8, and our expert weights get quantized as well. These are written to the inputs are written to row major layout on the left here, and then the expert weights are written to per expert column major layout. The reason for this is because basically a group gem conceptually is just a list of regular gems that are going to be executed. You can think of it as like literally a for loop through regular gems, and obviously there's like a highly optimized Cutlass kernel that parallelizes all this, but basically each individual gem that's part of this group gem needs to be independently valid and adhere to the memory layout requirements and all the other requirements of a typical gem. So that's why we do on a per expert, we have a memory layout of column major, not just the whole 3D tensor as column major, which is different, okay? And then, yeah, that's the quantization step. You can see for our scales here, these are our new scale tensors that were used to, the scales used to shrink the data, squeeze the data into the dynamic range of float 8, and then there will be used later in reciprocal form. Reciprocal scales will be used in the MXFP8 group gem to rescale the outputs of the dot products back to BF16 or your original precision, right? You can see they're fairly skinny here because, as we saw at the beginning, we use a 1/32 scaling factor, so the dimension we're scaling across is shrank by a factor of 32. Shrunken? Yeah, shrunken. I don't know. Yeah, so now moving on. I'm going to skip this slide because it's kind of redundant with this one, which is better, I think. We now need to do something unintuitive, which threw my mind for a bend, which is convert the scales to a blocked swizzled format, or that's what I call it anyways. I see it referred to as like a packed blocked format and other things, but basically it involves two steps. On a per group basis, we are going to convert each group's associated scales, which you can see the different colors here, into a blocked format, which means that it needs to be evenly divisible into 128 by 4 blocks. So we pad out rows and columns accordingly for each group, right? So each subtensor needs to have padding injected, so to speak. And then within each one of these 128 by 4 blocks, we apply a swizzle, right? And the swizzle is defined by NVIDIA. It's not one we just made up. It's part of the spec, and it's a requirement. And these requirements stem from this TC Gen 05, 5th generation tensor score MMA PTX instruction that we want to use for block scaled gems to actually, utilize the speed up in, T-flops per second that is achievable when using this format on Blackwell GPUs, okay? And some of the requirements it has are that one, the data or the scales live in TMEM. This is specifically the scales I'm talking about here. The scales live in TMEM, and that they're in this block swizzle layout, okay? And it's hard to find good information on why this is required and what the exact reasoning is and trade-offs for this layout versus other layouts. They have the NVIDIA documentation here, which is pretty sparse. It shows the layout, right? But then it just kind of defines it. It doesn't really walk through. Here's the swizzle. So here's the format, and here's the swizzle formula. And then it talks about how to combine multiple blocks, like they're in this kind of like row of blocks major format, right? But it doesn't really walk through like what specific performance problems is this solving. I guess I should mention that before we talk too much more, but where's the freaking presentation? Here it is. So after we convert to this format, another key part of it is um, you write it with block level granularity. You don't just write it into like row major or column major format. You write it in what I call row of blocks major on a per group basis. Because again, this diagram, everything is just for a single gem, right? But we're doing a group gem in which there is no documentation. And so we are forced to figure this out ourselves. Basically, we need to do this conversion on a per group basis and then write with block level granularity in row of blocks majors format, as you can see here in the blue, right? 0, 0, 0, 1, 0, 2, 0, 3, writing that first row of blocks, then 1, 0, 1, 1, 1, 2, or to the second row of blocks, and then we move on to our second group, right? And we do the same conversions, same swizzling formula, and then write in row of blocks major format. And the fun part is this is only valid for the forward pass. We'll see in the backward pass there's an even more annoying version of this. But anyways, my impression reading, there's also this Triton documentation that briefly touches on why the scales need to be in this format. And basically it's because in the inner loop over the K dimension, right, going through K blocks, computing we're accumulating these dot products and for the gem. We need contiguous access to 128 rows, right? That's the size of the block of scale factors for each subtile that we compute. This is matrix A that it's referring to here in this example. So basically, where's the freaking, sorry, God, I have too many tabs open. For like a 128 by 128 tile, the scale size for that 128 by 128 tile is 128 by 4, right? Because we've scaled, we divide by 32 along the K dimension, and then we want to be able to read in one contiguous, all this data, all these scales, we want to be contiguous when we move them from global memory into TMEM, right? And so if we write with block level granularity, this 128 by 4 block is all one contiguous chunk of memory, right? Versus if we had row major, then there would be gaps between these rows, right? It would not all be contiguous. These sub rows, so to speak, would be far apart in memory. Okay, so that's one reason. And the other reason, I think, for the actual swizzle in the TMEM, it's pre-swizzle before it gets to TMEM, but it's we move it into TMEM and it has a swizzle layout. I believe is because the actual TCGen MMA instruction, it's fetching very quickly during this inner loop over the K dimension, fetching these scales from TMEM rapidly as it iterates and repeatedly. And so it needs, we want to avoid bank conflicts. I believe would be the reason for applying that swizzle, right? So it's kind of a two-prong issue, is my interpretation for the requirement, the reasoning for this very unintuitive requirement, okay? And then the best part of all of this is that we cannot apply this, like I said, just to the whole tensor. We need to do it on these sub-tensor memory regions because we have to do it on a per group basis. And these groups are dynamic in size. And so on the host, as we are on the CPU thread running ahead of our GPU dispatching kernels, we don't know the parameters for the kernel. We don't know the size of the groups, basically, if we wanted to. So basically, to get around this without a device to host sync, without sending the group sizes to the CPU so it can start dispatching kernels, we implement custom Triton kernels to be able to read the group sizes. Because again, group sizes are dependent on router score computations, which are done on the device, not available on the host. So we need to have a kernel that can read these, read the group sizes from the device and perform the per group conversions here without a host device sync. And so that's what we have in TorchAO. And it works quite well. So finally, hopefully we've all wrapped our heads around this unintuitive conversion of our scale factors. Okay. Now we're finally ready to do our output. We're finally ready to complete our forward pass and do the actual MXFP8 group gem and have our routed expert output projection. So here you can see kind of what a decomposed MXFP8 group gem looks like. We have 5 experts shown here, but instead of a 3D tensor, I've kind of decomposed them into their, they're each just a linear projection, but they're stacked into a 3D tensor in real life. But you can see here each token group is map-mold with the associated expert, and then those outputs, which look like this, are conceptually just stacked into one output where we've now projected successfully each token to the projected to the hidden dimension. Okay. Now in the backward pass, I'm going to skip some of it because the gradient of the input is pretty similar to the forward pass. There's some different quantization kernels that you need, but it's still a 2D by 3D group gem like this one. So pretty similar. The interesting one is the gradient of the weight, which is actually now a 2D by 2D group gem where each of the inputs are 2D. Because we think about the gradient, the gradient of the weight is the transpose of our upstream gradient, which is a 2D tensor, right? It was we projected from m by k to m by n, right? So it's m by n. Transposed means it's n by m, right? And then x is still x. It's still just m by k. And I say total m here because it's all of the m dimensions for each of the token groups, right? These are like stacked. So this is just signifying this is the dimension in which we have the groups. Okay. So now, what does this change? This means that by the formula and by the structure of the matrices here, the groups are now along the contracting dimension instead of along like the rows, for example, here. So what does this change? Well, it changes everyone's favorite part, which is conversion of the scales on a per group basis to a block swizzled format. And so the main change here is, we still need to, on a per group basis, convert to a blocked format so that it is evenly divisible into 128 by 4 blocks. As you can see here, each color is a different group. So it must be evenly divisible into these 120 by 4 blocks. And then on a per block basis, we do the swizzle, as we talked about earlier. But now, it's a bit trickier where we have to kind of like, when we're writing with row of blocks major per group along K, before, the stride math was just a bit more intuitive because, row of blocks major is the same as just row of blocks, a row of blocks major per group was the same as just row of blocks major, basically, because the groups are along M. So even if we didn't know about the groups, we could just go through and write row blocks major, right? It's not quite true. We still have to worry about the variable size padding along the row dimension here, but just trust me, it's a bit easier with the pointer math in this version versus when the groups are along this way. The strides here need to account for the fact that the groups, the column size, basically the group size, is variable, so that when I'm writing, with a per block level granularity here, right? I need to know, okay, what is the stride for this particular group when I'm reading from my input tensor, and then write with block level granularity to this output tensor, like so, right? So you kind of have like these virtual strides here for these subtensors that we can imagine based on our group sizes. Okay. I think to really understand, you'll just need to look at the code. So feel free in TorchAO to look in the MoE training prototype directory, and there's a kernels directory, and you can look at it yourself. It was pretty interesting to write. You basically calculate like the stride per block and the stride per row of blocks for that group, right? Because we need to calculate if this group is like 2 blocks across column-wise, then what's the stride to get to the next, when we want to write the 1 by 1, what's the stride? And so it's variable per group, basically, depending on what thread block we are, right? So, yeah, pretty tricky. And then finally, so now, we've done our conversion to the block swizzle format. Now we can do our 2D by 2D group gem. So we have our 2D inputs, we've done our quantization and our scale conversion, and you can see what that looks like here. The groups are along the M dimension, or sorry, along the contracting dimension, which is M in this case, but Um, you can see decompose how it looks like here. You basically get these, what look like basically outer products where we have our um, uh, variable size inputs, but they're matched in because the group sizes are the same, right? It's the same group sizes applied to both operands, and you get these statically sized outputs as a result, right? Number of rows here, number of columns here, and then finally you can stack those. And what does that give us? It gives us a 3D tensor that's our gradient of the weight. Okay. And then here's all the various kernels we had to implement for this. You can see some various quantization kernels here because we need to quantize along different dimensions, different shaped input tensors in ways that are not necessarily generic, as you have seen. And then we need to be able to do the blocked swizzling conversion for 2D tensors, where groups are along M like so, and kernels for when groups are along K like so. And then also, we actually have to do that. I didn't go over it because it's simpler, but we have to do it for our 3D tensor as well. Those scales need to be in the block swizzle format. But there's no variable group sizes there, so it's a bit easier basically. So it's not as interesting to talk about. But yeah, and then we have our Cutlass group gem, MXFP8 group gem that's in FBGem we dispatched to. We wired it into torch.scale group.mm. And so yeah, I just listed some of the performance numbers here. These actually, the block swizzle formats, the kernels do not run with very good memory bandwidth utilization at all. But it turns out that the actual runtime is so vanishingly small that it really doesn't matter. Like I still want to go through and improve the memory bandwidth utilization, but it's like a vanishingly small percent. It's like 1% of the total runtime. Like it's just absolutely dominated by the actual gem. And then the I wish I had it. I wonder if I have I think I do. I'll show you really quick actually in TorchAO. I have a PR open. I did some roofline analysis and benchmarking to add to our documentation so people can see when it makes sense to use these features, when we'll actually get a speed up, when we'll get a slowdown. And yeah, so let's look at this one. So yeah, so you can see here, the top left is our roofline net speed up. The net speed up means like the MXFP8 group gem minus the overhead of the MXFP8 quantization. What's the net speed up from doing that? And you can see here that when our M dimension, number of tokens, basically local batch time sequence length, when that's small, we don't get much of a speed up or even a slight slowdown. But as it grows, we end up getting close to roofline performance. So we can see a gap here that we need to address for a smaller M dimension. So that's some more impactful work that I think needs to be done because look, we can just see immediately here kind of the issue. Like let's jump to the bottom right. The bottom right shows the kernel level breakdown of the total execution time of the forward computation, backward gradient of the input, and then gradient of the weight. You can see here it's hugely dominated by the what's it called? The actual gems, right? And the gems, now we look at the left, the 2D by 2D group gem here for MXFP8 is not achieving that great of a speed up relative to the 2D 3D group gem, right? The 2D 3D group gem is hitting close to 2x speed up or even slightly higher than 2x, which is actually just indicative of the BF16 baseline being a bit weaker there. We shouldn't be able to achieve higher than 2x, but basically it's around roofline performance, right? It's getting close to 2x or slightly above. Versus the 2D, I mean, we're at like flat or only up to 1.6 in one case, and then back down to like 1.15. Like, I mean, this is a pretty big problem. So we need to, this is a much more important, because if the gem is not significantly faster, none of the quantization kernels matter, right? Like the whole idea is for this gem to be close to 2x faster, and then that provides enough of a gap, like we saw in our original slides here. It provides enough of a gap for us to work with that we can squeeze in the quantization kernels as necessary to then get a net speed up, right? So that's the highest priority. I don't know where this went. But yeah, you do see the there actually is okay. It's actually a bit larger than I thought. Than I remembered. The contribution of the scaling conversion kernels to block format. Um, yeah, you can see here we get like 80-90% memory bandwidth utilization for quantization kernels. 2MX is not actually used. This is just a baseline in Torch native code. And then the blocked formatting kernels are atrocious in memory bandwidth utilization. And part of that is just it's like a naive Triton implementation that I won't go over in detail, but it was very hard just to get it functionally correct with numerics, with all the issues I was describing earlier with this stuff, all this tricky point arithmetic, and the lack of documentation for group gem. There's only just like regular gem documentation. Even that is like pretty sparse. So I was pretty happy we were able to achieve solid net speedups as an end result with this, even with the scaling format or scale conversion kernels not being optimal. So these are the numbers again with the current kernels, um, and so next step, optimize the scale conversion kernels, optimize the 2D case of the MXFP8 group gem, the Cutlass kernel there, and then we should get even more significant speedups. So yeah, stay tuned for that. And that's basically it. Yeah, we're also working on, like I mentioned, the all-to-all, making that you know more performant by making output desequalization optional, making a token shuffle kernel that can shuffle the group gem or shuffle the MXFP8 inputs. And then we're also working on FP8 blockwise support for everyone using DeepSeek v3 based models, which uses kind of like blockwise quantization for Hopper architectures. So yeah, I've talked for long enough at this point, so I'll end the recording here. And yeah.